So, like I said yesterday, we're going to dip our toes into calculus today, just for a little bit. Okay, just so you can kind of see a little sneak peek. And the way we're going to do that, or kind of get our introduction to it, is to discuss the slope of a function. So first of all, we'll start out with a function whose slope we will know. So let's consider f of x equals 2x plus 1. What is the slope of this function going to be? No trick question. What is it? 2. That's right. 2, right? Or as a fraction, right? We could say like 2 over 1. If we want to, we can also like graph this thing. Let's see here. Alright, so we know we have like a y-intercept of 1. We're going to go up to right 1 then, and then we can also go like down to left 1 as well. Okay, there we go. And so to find the slope of this function, right, we have lots of options available to us. One, we can recognize the function is written in slope-intercept form, right? That first of all, it's a linear equation, and it's written in slope-intercept form, so we can just pull that slope of 2 right out of the equation. Alternatively, looking at the graph, right, we could pick 2 points that are on the graph, use that slope formula between those 2 points, right, y2 minus, well, bless you, y2 minus y1 over x2 minus x1. Evaluate that, and that can give us the slope as well. Or you can just count, too, right? You can just count the rise over the run. Lots of options here. Okay. You can say definitively that the slope is 2, and it will be 2 everywhere, right? The slope of a line never changes. It's always 2. Right. Another idea that we have also of the slope is the rate of change of the line, or the rate of change of the function, I guess. So, you know, we could say that, you know, again, a line has a constant rate of change. It's flat. The slope is always just 2. No matter where you are, the slope will always be 2. All right. Plenty of time spent on that kind of stuff, right? Now let's consider a different kind of function. Negative x squared plus 4. Alright. And what is the slope of that function? Well, now it's not so clear, right? This is no longer a linear equation, right? It's a quadratic. So it's going to be a parabola that we get the shape here. Let's go ahead and just sketch a quick graph of it too. Why not? Okay, so to sketch the graph of this thing, well, that plus 4 on the end means we're going to shift things up 4, right? The normal graph of x squared has its vertex at 0, 0, but it's going to be shifted up 4. So our new vertex will be at 1, 2, 3, 4, right up here. And then because it's negative, right, we know we're going to have kind of like a bell shape instead of the U shape, right, the bell kind of thing. So I'll just plug in some x values here. Let's plug in like 1. 1 squared will be 1. Negative 1 is, well, negative 1 plus 4 will be 3. So at 1 we should be at 3. And then because of symmetry, we'll also be at negative 1 will be at 3 as well. We can do 2. 2 squared is 4. Negative 4, though, will be 0. So it's 2, 0. And then negative 2 will also be at 0. And I'll do one more here. I'll do 3. 3 squared is 9, but it'll be negative 9 plus 4, so negative 5. So 3. So 1, 2, 3, 4, and 5 would be like right here, I guess, something like that. And again, same idea over here with this 3. Okay, so we're going to have a graph something like that. Okay, again, very familiar kind of shape. But now looking at this, it's still kind of weird to ask the question, what is the slope of this thing? Right? Because it's like curve, it's not like a straight line. Well, believe it or not, you guys have kind of an intuitive sense already, an intuitive understanding of what the slope of this thing would be. For example here. Well, let me go back up to this line right here. So we have some other things that we know about this from this line too. Since the slope is a positive 2, right, that indicates that our function is increasing here, right? Like it's going up from left to right. A positive 2 indicates a positive slope is going up, goes up from left to right. Whereas a negative slope, right, we also know would go down from left to right. Right, but that's not what we have, a positive slope. We can also talk about the slope number too, right? Like a bigger slope value, for example, like 3, 4, 5, those numbers, they are steeper, right, than things like 1/2 or 1/3 or 1/4, stuff like that. And of course, the slope of 0, it's not positive or negative, so it's like completely horizontal. The slope of 0 would be horizontal. Well, when we think down here to something like this, right? For example, at this point, if we were to think of the slope at this point right here, would it make sense to say the slope here is positive, negative, 0? What do you say? What do we think?
Negative.
Negative. Why?
It's going left to right down.
Yeah, it's going down from left to right. Okay, yeah. So we'd indicate like maybe for this entire section, right, since we're going down from left to right, maybe these would all be like negative slopes. And you'd be right. We don't know why you're right yet, or that we can't really prove it, but I can tell you that you're right. There's it. That's right. All right, cool. So then, what about a point right here? What would the slope be at this point right here? What do we expect? Positive, probably, right? Because again, it's going up from left to right. So yeah, these are like positive slopes here, because the function's kind of going up from left to right. And in fact, there is one point on here where we can for sure say the exact value of the slope. And that's right here at the top. What do you think the value of the slope is here precisely at the top? It's going to be 0. It's going to be a slope of 0. So right at the top, slope is 0. So for some points on our graph, we're going to have positive slopes. For some points on our graph, we're going to have 0 slope. Sorry, for a point on our graph, we'll have a 0 slope. And then for other points on our graph, we'll have a negative slope. So the question, what is the slope of this function, is a bit misleading, right? Because the slopes are changing depending on your location on the graph. So we go from a line whose slope is always 2, no matter where you look, to a quadratic function, and in fact most functions, where the slope is varying, changing, depending on where you are on that graph. Okay, so then the question arises, how do we find the slope of a function at a single point? That's a weird concept. We know how to find the slope of something if we have 2 points, right? That's how we find the slope of a line, y2 minus y1 over x2 minus x1. But how can you find the slope of something if you only are trying to use a single point, right? Because every point on there is a different kind of slope, potentially. Okay, or how do you find a slope for the function? So this is where we're going to use the idea. This is where we introduce the idea of the derivative. Okay. So the derivative is a limit used to find the slope of a curve. Okay. The process of finding a derivative is called differentiation. Okay, so Find a derivative, take the derivative, differentiate. Those are kind of synonymous ideas. Okay. And this is calculus. This is calculus. All right. The way we denote the derivative of a function, or one way to denote the derivative of a function, is to take that function, right, because they're so closely related, right? The derivative directly tells us lots of information about that function. Okay? So they're closely related. So the way we denote the derivative of a function, or sorry, one way to denote it, is you put a little apostrophe here. Okay, and that's called f prime of x. F prime denotes the derivative of the function f. And the way we find that derivative, which is kind of what we've been, leading up to here, is we take the limit as h approaches 0. So now you can see, right, why we had to wait to learn this kind of thing. The limit is h approaches 0 because we just learned about limits of f of x plus h minus f of x all over h. So the definition of the derivative is merely the difference quotient with a limit attached to it. It's the limit as h approaches 0 of the difference quotient applied to your function. Okay. So anytime you did a difference quotient in this class, right, you were like 90% of the way to, doing calculus. You just didn't know it. Okay. Now, why is this thing the derivative? How does this thing end up being the derivative? Well, the difference quotient, this limit, is essentially the slope formula. All right, and I can go into more detail about this during set if you want to. If you want to come in or something like that, we can discuss it. I can show you exactly what's going on here. But you can kind of see the slope formula right now. I'll just do like a quick little, thing here. I'll show it to you. You can kind of see the slope formula there, right? If I have that f of x plus h minus f of x, well, you can see here's your kind of like your y2 minus your y1, right? F of something, that's a y value, right? F of another thing is another y value. What you may not be so clear to see is like, well, wait a minute, you just have h. Where's the x2 minus x1? Well, if we take our x here of x plus h, and we subtract the x here of x, what happens to the x's in the denominator? They cancel, and you're left with just h. Okay? So this thing is the slope formula. But wait a minute, Mr. Meyer, how are we using the slope formula that requires 2 points to find the slope of something at only 1 point? Well, that's a question that I'll answer if you want to come in for set to answer that, okay? Or you'll definitely see it next year if you see it in calculus, okay? But I don't want to spend more time on that, so. Let's do it. So let's find the derivative. And let's first find the derivative of that linear function, f of x equals 2x plus 1. Okay? If the derivative finds the slope of a function, right, that's what the derivative is supposed to do, a limit that we use to find the slope of a curve or slope of a function. If the derivative finds the slope of a function, what had we better get for our answer here? Better get 2, right? 2 is the slope of this function. We know that, so we better get 2. So let's see what happens. All right, so we'll take the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. So again, this thing can be kind of a pain in the butt to like fill in and stuff like that. If we take it in pieces, though, we can it makes it a little more palatable. The f of x, right? We already know what f of x is. It's 2x plus 1. So I already know this piece of the derivative. But I need to find what f of x plus h is. So let me go ahead and do that little side calculation here. F of x plus h is 2 times the quantity x plus h plus 1. Right? If f of x is 2 times x plus 1, we'll just replace the x with x plus h. And now we'll fill in our difference quotient here. So the limit as h approaches 0, f of x plus h, 2 parentheses x plus h plus 1, minus f of x is 2x plus 1. And again, minus the quantity f of x. So make sure you put parentheses around that f of x. And then all over h. Okay, so any questions on just that substitution there? We good? Okay, so now we just simplify. The 2 would distribute, make it 2x plus 2h plus 1, And then we'll distribute the minus sign as well. Minus 2x minus 1 all over h. By the way, we could attempt to evaluate this limit right now. We could, if we wanted to, just do a direct substitution. But if I direct substitute it in 0 at this point, you get 0 over 0. Indeterminate form, right? So we actually need to continue simplifying here. Okay, so if you plugged in 0 for h here or here, you get 0 over 0, indeterminate form. We need to keep simplifying. So how can I keep simplifying here? Does anything cancel? The 2x's. Anything else? The 1's. And so we're left with the limit as h approaches 0 of just 2h over h. But then what cancels now? The h's. And oh my gosh, it's 2. It's pretty neat. Okay. Of course, we could have just read that from the line too, but now we use calculus to do it. Okay. Okay. And again, in this case, at this point, there's no place for us to plug in 0 for h, right? All the h's are gone, and so we can just evaluate the limit and say, well, okay, it's 2. It's always 2. So that's not very interesting, though, right? Because we already knew this answer. Who cares? Okay? Let's do something whose answer we don't know. All right? Let's not spoil things for ourselves. Let's now find the derivative of that other function we mentioned. Negative x squared plus 4. Okay. Let's see what happens here. So again, the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so again, to evaluate this limit, we have this piece. We know the f of x piece. We really should. I'm going to do some side work here and evaluate the f of x piece, or f of x plus h piece. If you're comfortable with like just doing that substitution, please feel free to do it. You don't need to do side work if you don't want to, but if you find yourself getting confused or stuck, you want to do this little bit of side work where I write both f of x and then I evaluate f of x plus h. Okay, and now I can sub it in. So instead of f of x plus h, I'm going to write that negative quantity x plus h squared plus 4 minus, and then f of x. Again, it's minus the quantity of f of x, so parentheses around that when you plug it in. Okay, so there's substitution. We good on that? Questions on that? Okay, so far so good? All right. So, and again, just stop me if you get lost. We have to expand out this x plus h quantity squared. So, x plus h quantity squared is going to be x squared plus 2xh plus h squared. I'm also going to distribute the minus sign here in front of the parentheses, so it'll be plus x squared minus 4 all over h. We have a minus sign in front of parentheses, so we're going to distribute the negative. Negative x squared minus 2xh minus h squared plus 4 plus x squared minus 4. Okay. So, does anything cancel here? X squared. So you have a plus x squared and minus x squared. What else? 4s. Okay, so let's rewrite things here. Negative 2xh minus h squared over h. Okay, so things canceled. But if I still try and do a direct substitution here, I'm going to get 0 over 0, indeterminate form. And I can't, if I plug in 0 right now, my last step there, I'm not going to get anything useful. How can we proceed from here to simplify this? Can we simplify? Yeah, Maddie? Good. And I like that you factored out the h. Yes. Let's factor an h out from the numerator. Okay, so now we can cancel with the denominator. right? As was written, right, so we have subtraction between these two things. I couldn't just cancel the h out with one of these h's here. I need to take an h out from both terms to then be able to cancel out totally there, like that. And so now you've got the limit is h approaches 0 of negative 2x minus h, which means the derivative is negative 2x. Right, when you plug in that 0. Okay, you get negative 2x. Weird. We didn't get a number here. I mean, we got a number, we also got a variable. Okay. But this should make sense. Let's go back to what we said before, right? So let's take a look at our earlier picture that we had, right? We said that the slope right here at the peak was 0. Well, what's the x-coordinate of this point? And if I plug that x-coordinate in here, 0 times negative 2 says the slope is 0 at that point. 0 times negative 2, that's the slope is 0. Okay. What about here? We said the slopes here were all going to be negative. So if you pick any point along here, I'm just going to pick this one. The x-coordinate here is 2. If I plug in that 2x coordinate here, 2 times negative 2, negative 4. The slope is negative. In fact, it's not just negative, it's negative 4. We know exactly the slope at this point. The slope there would be, at this instant, is negative 4. Likewise, we can just go over here where all these positive slopes we said would be, right? Negative 2 is the x-coordinate here. Plug it in, negative 2 times negative 2, positive 4. So the slope here is positive 4. So not only do we have, the right slopes, but it's also like symmetric, just like the graph is, right? A negative 4 slope here, a positive 4 slope here. Very interesting. Very interesting stuff there. Okay? So this thing, right, that we simplified down to, this derivative, it's dependent on where we are located on the graph, the x-coordinate specifically where we're located. And we just multiply the x-coordinate by negative 2, and that will give you the slope at any particular point. Okay? Or the rate of change of that function. Pretty neat. Questions on any of that? All right, so then you're going to have 3 to try for homework. So, out of the book, page 901, numbers 53, 56, 75. Okay? Here's the bathroom. Yes. Ooh, not yet. There will be the test. There will be questions on the test. I think how you do. Yes. Or at least a question. This will show up.